So shall we start? Hi, everybody. So, yep, we ended up here last session, right? So we ended up talking about overfitting, and we talked about different, say, points of view that we can describe the reason that we are having overfitting, right? So there were three main points of view we talked about. The first one was the obvious one, which is why we have overfitting. The model is too complicated, yes? So we have a large capacity model. This is the first thing that we can say. The second thing is that, I mean, if we just say, okay, we're fine with this model, we don't want to change it, we could say instead that we have, what is the second point of view or second reason? Too small amount of data, right? So we don't have enough data, so because of that, we're just overfitting to that small amount of data that we have. And the third reason, which was a bit of more complication, was co-adaptation, right? So you remember what was co-adaptation? How was the behavior? So we talked about this dummy example that wanted to just fit an order 5 polynomial into a data collected from order 2 polynomial, of course with some sampling noise or measurement noise. And then when we started doing the training, up to some point we were getting into a kind of weight vector, which is pretty much the same as this W star that we are looking for. So this W star, this is the target one, which describes the ground truth, right? The one which we don't have access to. And the ground truth, if you remember, it was this function. So your label V, I mean, it was not the label in your data set, but your label V was some original, say, V prime plus some error. So you got some error. And this V prime was 3x squared plus 3x plus 3, right? And then we said we can look at it as a vector of or a polynomial of order 5, and then W0 here is 3, W1 is again 3, W2 is 1, and everything is 0. So 3 zeros here. So this is how we define this W star, yeah? So we talked about this, that this guy is the ground truth, but of course we don't get into this one because basically what we are sampling is a noisy version of what the true model is, right? And then if we start just training this order 5 model into this particular data set that we collected, up to some point we're getting close and close to the target function, the ground truth. But at some point when we keep on training, then we are getting into something worse, right? So we're getting close, so this curve somehow explained this one. So we're getting close to the target, the ground truth, but at some point we're just getting away from that. Clear? And the main reason was this idea of co-adaptation. So we said we have the samples which are noisy version of the ground truth, and then what we try our best to get fit into those samples. And up to some point we're just getting close to the envelope, which is the true function, this quadratic function. But when we got close enough to that quadratic function, since we still keep on training, we try to just fill the gap between the noisy version of the samples and the ground truth. And that's going to make us somehow overfit at some other points. Clear? So this is the idea of co-adaptation. So I think we talked about this idea. This is pretty much what I told you. So those three main components, W0, W1, and W2, I mean the first three components in this polynomial model, they are basically the one which are presenting your true model. And the other three things are the ones which are somehow fitting to your noise, but they are not somehow distinguished, right? So when you try to just fit the other three, then you somehow make the first three diverge from the ground truth. And this is the idea of co-adaptation. So it means that, so it's like you have a bunch of points, and then you try to fit something by, I don't know, a rope or something into it. Then when you push one point up, then the other one automatically gets down, right? So because of that, you just try to fit into the sample that you have, but then you get away from your true function at some other point. So this is the idea of co-adaptation. This is one other reason or one other point of view at the overfitting. And this is the most common point of view that you have usually. Because usually in practice, you're going to detect overfitting by doing such an experiment, right? I mean, in practice, you never have access to this W star because you really don't know what is the ground truth machine, right? So this is a dummy example, but in practice, you don't know that this is coming from a quadratic function. You just know some samples. And then at the end of the day, you cannot say how far away you are from the ground truth. You never can say it. But you can see such a behavior. Like you start doing the training, and then your empirical risk during the training is always going down, which makes sense, of course, right? So it just, the more iterations you do, you better fit to your model. But then when you try to plot the test risk, you're going to see that this guy comes down up to some point, but then it starts to go up, meaning that your model is just failing to generalize the more you train. Yeah? And this is the most obvious thing, or the most practical way of detecting that overfitting is happening in on my model. Clear? Okay, so if I want to just summarize everything, so we have three main reasons: large capacity, small data set, and co-adaptation. And as I told you multiple times last session, I again indicate that these are not like independent reasons. Like this is not, overfitting happens when I have 1 or 2 or 3. I mean, when I have 1, I basically have 2 and 3 as well, right? But it depends how I look at it. So I don't want to touch my model, but I can deal with the data, so I'm going to increase. So I'm going to look at the overfitting from the second point of view. So I say the main reason is that I have small amount of data, so I'm going to increase my data, yeah? Or I cannot do anything to my model or data set, then I'm going to somehow find a way to get rid of that co-adaptation, which is the regularization idea, okay? So these are mutually dependent things, and this is a kind of sentence I tried to just summarize this whole point into it. So when you have a large capacity model, then, for example, a very deep neural network with too many neurons, then the thing that is going to happen is that whatever you are training, given the data that you have, you're basically training on a sort of a small data set. And this can lead to overfitting, especially if you keep on training for a long time, right? The more you go on training, the more you get into the overfitting issue, and you need to get a kind of solution for that. So now, the question is how we can deal with overfitting, how we can get rid of it, yeah? And if you remember, I mean, we talked about the very basic idea of validation at the very beginning, right? So we said that we can do validation, meaning that we could just try to change our hyperparameters, which essentially just specify the model capacity, and then we try to just validate, so we just check out what's going to be the final validation risk, and then we take the one which gives us the minimum risk, right? And hopefully it's going to prevent us from overfitting. But as you probably got it by now, is this one is not that much practical. I mean, in terms of overfitting, because you cannot really start from one hidden layer and then you keep on with 100 hidden layers, right? So this is pretty much a nightmare. I mean, the whole computation goes forever. So this is not something that you're going to do for every single hyperparameter you have in your neural network. But if you just fit yourself into or fix the first point of view, this is going to be the solution. But what about the second solution, point of view, sorry. So if you don't want to change your model, say you have done some validation, you have chosen, there are a bunch of main hyperparameters, you fix them, you just found the best one of them, but still you're seeing overfitting. I mean, this is totally possible, right? So the next thing that you might say, okay, I have not enough data, right? So I need to increase data. And then you might say, OK, I'm going to go out and collect data. So this is not something we do in this lecture. So we assume that we have done this before, right? So we do not have access to more data by just going out and collecting them. So then there is the idea of data augmentation, which we are going to talk about this, hopefully today. Okay? The idea is mainly that, simple words, if you have an image of a cat, then if you rotate it, it's still a cat, right? If you reverse it, it's still a cat. If you squeeze it, if you just zoom it out, whatever you do to that, it's still a cat, right? And you can add all of those cats into your data set and label them with cat, right? Now you have more data. Yeah? So this is the idea of data augmentation. We're going to talk about this today. So this is one other idea, but of course, I mean, you can do some of data augmentation, but again, this is not going to just give you a huge boost in terms of overfitting. So say you did the hyperparameter tuning, you just did this guy as well, and then you still see the overfitting. Yeah.
Yeah. So for data augmentation, for me, it doesn't seem like to make sense because it's the same information, right?
Sorry?
It's the same information that you are.
It's not the same information. You can just, I mean, we're going to talk about it today. But you can add, for example, a bit of background noise to it. Yeah. You can change it. I mean, this is not the exact information. And one other thing is that your neural network is actually very dumb. So you're not really, it cannot, if it could detect the, very instinct, very summarized version of the information available in your data, you wouldn't need to go through all of this. Yeah. So it's going to help, of course, even if you add those rotations. But as you might guess, it's not going, in many applications, it's not going to gain you a huge thing. But it can improve it. It can. Yeah. So, but say that you have done these two, and this does not, I mean, these two still are not resolving completely your overfitting, then the other idea is to just go for what we call it regularization. So regularization, it means that try to make a sort of trick in your training process, so that you make sure when you keep training your model, it never goes inside those regions where co-adaptation is harshly happening. Yeah? So we want to just avoid that. And this is the idea of regularization, which we are going to talk about next. Okay? So, any questions? Okay. So what we have done up to this point, we do know how to do hyperparameter tuning. Nothing specific about that, right? Just choose your parameter, try, then validate. And about data augmentation, we are going to talk about hopefully today, as I said, but next thing that we are going to talk about is regularization. So since you're fresh with co-adaptation, let's go with regularization. Okay. So what is regularization? As I told you, regularization is a kind of trick, say, call it, or a method that you are just doing it in order to avoid overfitting when you look at overfitting from co-adaptation point of view. Yeah? Or basically you want to suppress this co-adaptation property inside your training loop. So how we can do it? Let's just get back to the idea that we have and I mean the simple example that we had. And the simple example was this, polynomial thing. And what we did, if you remember, as we talked just a few minutes ago, we started with polynomial order 5 and tried to fit it into the data that we sampled from this machine, right? And we saw the co-adaptation behavior happening, overfitting happening, things like that, right? Now, let's just get back to this, and first of all, let me just write down you the three things. This is the initial weight that we started with in the model, and then we kept on training up to the point where we got into WT2. And that thing W0 that I have it on the board for you was the target. So somehow intuitively we set up to WT2 or after T2 iterations, we get into a vector which is quite close to that one, right? But that is not exactly this one. But we insist on training, and then we get away from that, right? Clear? Now, so what can I say about empirical risk that I have? So say I have empirical risk r hat. This is the thing that I am going to minimize in order to train my neural network, right? So I go on and compute this guy at W0, at WT2, and at WTN. Now, can you tell me which one has the maximum value? At 0, right? So this guy is more than both of them, right? So this is the larger one. What about this guy? Is it more than this one or smaller than this one? More than this one, right? Because we were at time t2, and then we kept on training, we got here, right? Meaning that we were just still reducing the empirical risk, right? So this guy should be also more than this one, right? So you do agree with me that this happens, right? So the smallest guy is the one which get at time tn. The largest one is the initial one, of course, right? This was what happened when we were training. Now, one thing that you can look at this, these vectors here, which one has the largest amplitude? If I compute the second norm of them, which one do you think has the largest second norm? Tn. Tn is just having a very large values, exactly. So this guy is going to have larger second norm, yeah? So what I can say is that the L2 norm of WTN, say squared, this guy is more than or equal by, it's more than, absolutely in this example, is more than T2, second norm. And then this is again W0, right? So this guy is having more amplitude, larger weights as compared to this one, as compared to this one. Now looking into this, let me see, yeah, this is, so looking into this idea, what I can do, I can say for example, I give them some numbers. For example, I assume that this guy is 0.001, this guy is 0.01, and this guy is 100. Okay? This makes sense. I mean, I started with 100 risk, then I reduce into 0.01, then I reduce to 0.001. And one thing that I'm seeing is that the weight is just increasing, right? So what's going to happen if I add up this guy into this value? Do you expect that you see again this decreasing behavior necessarily?
Sorry, maybe in this example we have a larger second norm.
Yeah, just for the moment for in this example. I mean, we talk about that later, okay? But just for this example, if I add up this guy to this one, and I add up this guy to this one, and I add up this guy to this one, do you expect to see necessarily this behavior that this after summation they are just dropping? Not necessarily, because this guy is larger, yeah? Potentially it could be much larger than this one, so that when I add it up to this 0.001, the summation is getting more than this one, right? This could happen, correct? So this is what we are observing. So if we just implement the observation I explained you here into numbers, then you're going to see this behavior. So if I just get this r hat and add it up to the norm of the weights, then you're going to see that for the first one it's going to be 100 because the norm of this guy is absolutely 0. For this one, this is going to be this guy because this is 19.03, and this guy is much larger, so 44.76, so this is going to be this one, right? Now, among these three values, which one is the smallest one? The middle one, right? So if instead of minimizing r hat, you give this new r hat plus the norm of the weight to your gradient descent algorithm and ask it to just minimize it, what do you expect? If you start from W0, you could potentially get to WT2 because that guy has a smaller sum as compared to W0, right? But but you would never get from T2 to Tn, WTn, right? Because that one is increasing, correct? So this is what you're going to see. So penalize, if you just penalize that risk, which is this guy, with the norm of the weights, then the thing that you are going to see is that you could potentially get from W0 to WT2. So you are still getting from your initial point into the point where you want, but you are not going to get into the point that you don't want to see the behavior. Correct? You got the idea? So this is the idea of penalizing. It means that you just give a penalty for your training loop if it goes towards the point which you intuitively know that it's not the right place to go. Yeah? And by doing that, you make your gradient descent to just go towards the point which you think is a good choice. Correct? Everybody's clear? Yeah? So this is what we call it the idea of regularization. So regularization idea, it comes from, I mean, it's not nothing specific. You get your penalty that you want, or objective function that you want to optimize, and then you add up a penalty into it, cite that that penalty imposes the behavior that you want to see. Okay? So usually when you do training with regularization, you have such a thing. So you have your empirical risk as before, as you have, and then you have one penalty function pi. Okay? And this pi is just mimicking the behavior that you expect to see. Now back to the question your friend asked. Here we just did now that if we are, I mean, we just tried a couple of times. I mean, there is a bit of more theory behind it, but we tried a couple of times. We have seen whenever we are overfitting, we're getting into large weights. So what we intuitively know is that we don't want to get large weights. So it's better to just regularize it by the weights. Yeah? We could have potentially other things. Yeah? You might know out of some intuition or maybe out of some property that the problem has that you should see something else, right? And then you can try to design a penalty function pi such that that guy imposes this behavior that you want. Clear? Everybody's clear? So you got the idea what is regularization? Okay, so this is pretty much one of the, say, best approaches you're going to do when you want to just deal with overfitting in your training loop. Because anything else that I showed you, I mean, data augmentation or the other guy, hyperparameter tuning, they are nothing that you do within your training loop, right? So when it comes to training loop, the only way that you can do it is by regularization. Clear? Yeah.
Sorry, I understand that we always try to minimize the weights. Am I right? In every cases.
You mean risk, not
Be large. Yeah?
here?
Yeah,
You
the
mean?
pi.
The pi, I mean, it's not necessarily the amplitude of weights. I mean, it could be different things.
Yeah.
It could be a weird function. It usually, I mean, there is interpretation why that x squared, second norm makes sense here. I mean, if I want to be very strict, you could say if you are doing maximum likelihood estimation, then what you're minimizing is actually the likelihood. And then that other term, when you write everything in log scale, then that's going to be the log of your prior distribution. And if you assume that the prior thing is Gaussian, which makes sense because you don't have any idea about that, then it's going to show up to be L2 norm. And then L2 norm has a kind of, probabilistic meaning as well. But these are only justifications, right? So at the end of the day, the thing is that, like, when you try it so many times, you observe that, whenever your model is overfit, then the weights are extremely large in amplitude. And then you get the feeling that, okay, the amplitude should not be that large, and this is why you just add it up here. Yeah? So this is a very basic point that people started with. But of course, you could have more concrete justification for that. Yeah, you wanted to?
I was about to ask the second question.
Oh, okay, great. Okay, so Everybody is clear now about the regularization? So it's not a kind of weird thing. Yeah? So you just have your risk, you add up a penalty function. And that penalty function, the regularization term that you're adding up, this is something that if you're engineer, you're going to get out of textbook. If you're a scientist, you're going to just look at your problem, try hard to find out what that function should be. Yeah? But at the end of the day, either your intuition or the textbook needs to tell you what is that pi function. Correct? Clear? Good. So there are some versions of this pi function which are very well known. One of them is like this L2 norm that I told you here. This is Tikhonov regularization, very old form of regularization. I guess this is one of the first ones discussed like during Cold War, because Tikhonov was in Soviet Union. Definitely, it was before, during the Cold War time. So this guy is simply the L2 norm. I mean, the original one, you can also multiply that W into a matrix. Yeah? But practically, we usually just use this one. Okay? And as I told you, there is some probabilistic intuition behind it. So if you have no clue about your weights at all, you don't know how your weights should be distributed, where is the range of their numbers, probably you choose this one. Because this is proportional somehow to the Gaussian prior belief. Like, you have no idea. Yeah? Nothing. You don't know anything before seeing the weights. Okay?
Can we interpret this one as another thing? For example, first of all, we consider 10 weights, but for the second norm, we are trying to use at least as possible. For example, we are trying to use 3 of them.
Yeah, this is going to be the second one. I mean, this is somehow proportional to that, but this is a very approximation of what you are, a bad approximation of what you are thinking about. The other one is this Lasso guy. Okay, so this is the second regularization function that you can add, and now you're adding, instead of L2 norm, you're adding L1 norm, meaning that the sum of absolute value of all weights. Okay, and this is what we call it lasso. Anybody knows what is lasso? Lasso in English. There is a rope you just take to get the horse, right? But this lasso is not that lasso. It was the trick. It's abbreviation of least absolute shrinkage selection operator. And do you know who has proposed it? Come on, you're at U of T. No. It's older than all of this. Is Robert Tibshirani. He is not right now at U of T, but when he proposed this, he was a professor here at the Department of Statistics. So just search his name. I mean, if you search Lasso, first Wikipedia comes is about Lasso, and then you just click on Robert Tibshirani, you're going to know him. Okay? But the idea here is that what you want to do, so it's a very old thing, actually initially developed for geographical contours. So what you want to do here is that you want to just restrict the number of entries inside your model which are non-zero. So you want to have lots of zeros within your weights. And why we should do that? Because we do know that overfitting basically comes from the fact that our model is very complicated, right? It means it has too many weights, correct? So if we can get rid of some of them, then probably we are reducing the capacity of that model, and then we avoid overfitting. Makes sense, right? And then how we can restrict the number of non-zero entries inside our weights, I mean, if you want to be very concrete, you should put instead of L1 norm, L0 norm. But then that's going to make your optimization problem infeasible. You cannot compute the derivatives. And this is why you go for L1. So L1 was shown by Tibshirani that is the best convex function or convex penalty that you can add to your risk, such that you restrict the number of non-zero entries. Clear? L0 norm is like just you count the number of non-zero entries inside your vector. Okay? So it's not a convex function. It's not even a real norm. So we just call it. But you don't. It's like an indicator function. Yeah? So instead of having this guy, you should put the number of non-zero entries as the penalty. But that's going to make your training infeasible. Everybody's clear? So this guy could do much better than that one, when you do really know that you need to restrict the number of, like extremely restrict the capacity of your model. Just get rid of some weights. Clear? Everybody's clear? Any questions? So that was the idea of regularization, but one regularization that we practically most of the time use in our implementation is dropout, which is neither Tikhonov nor L1 norm, but it's somehow related to that L1 norm idea. So now this dropout is now proposed by Geoffrey Hinton. Okay, so we're back to 2012. So now, what is the idea of dropout? So basically the same thing as L1 norm. So you want to get rid of some weights. You do know that you don't need all of the weights inside your neural network, because simply when you put all of the weights non-zero, like here, then it's going to just overfeed. Yeah? And you want to get rid of some of them. But which one you should get rid of, you don't exactly know, of course. I mean, if you would have known, you could get rid of them at the first place, right? So what you do here, the idea is that, okay, let's just do some random dropping. So when I start training my neural network, in the first, for example, iteration that I'm doing, or first forward-backward pass that I'm doing, I just randomly set some of the neurons off. Yeah? I just put them 0. I do my forward-backward, so I have done it on a reduced model, right? And then when finished, then I want to compute my next gradient sample, right? Again, what I'm going to do, I'm going to randomly turn off some other weights, neurons. And then I again do the forward-backward. And I keep on doing this till my training is over. And then hopefully this is going to average over all reduced versions of my neural network. And then it's going to get trained the way that I do not see overfeeding. Okay? So I hope that this basic idea was clear, but let me just show it on the curve, on the diagram for you, so that you get the idea concretely. So say that you have this, for example, neural network, 2 hidden layers, 1 output layer, 1 input layer, and you want to do training. What you're going to do, say for the moment, assume that you have you're doing sample level training, okay? Meaning that you are not doing any mini batch, right? Mini batch size is 1, okay? What you're going to do, you're going to start with your first data. You just go forward over all these lengths. You get to your output. Once you got there, you just pass backward towards your input. And once you're here, you can compute your gradient with respect to all weight matrices, correct? And you update. Yeah? Now, if you want to do, then when you go for the next iteration, what you're going to do, you get your next data point, you do the same thing, you update, and you keep on going, right? Now, what you do with dropout is that when you start with your first data point, before you just go forward, you just randomly drop some neurons, some of these nodes. Meaning that you say, okay, here the second one is really there, but now I assume that my second input is not there anymore, so it's off. Yeah? When it's off, when it's 0, I don't really need these weights anymore, because in the forward pass, 0 got multiplied with all of those weights. It's going to be 0, correct? So I can drop it out, right? Same thing with this neuron in the first hidden layer, right? So I would say this guy is off, meaning that this is not sending anything forward, right? So I'm getting rid of that neuron as well. And I do it to a bunch of them. So I randomly choose 1 neuron, for example, here, 2 neurons here. I don't know, here I have not chosen, so all of them are here, all of them are here. So I just randomly do it, yeah? Out of chance, in the first one, this guy got dropped out, this one, and this one. And then when I'm over with forward, backward, then I go for the next data. And again, before I sending forward, I am going to just randomly drop out some other nodes, okay? So this time, instead of the second one, I'm dropping out the third one, right? Here also, in the second one, I'm dropping the middle two, right? And so on. Like in that one, I'm just dropping this guy, and this guy, and this guy, and so on, right? And I, again, do the backward pass, and I compute the gradient, and I update, okay? And I keep on doing like this till my data is over, yeah? And then when my data is over, what I can imagine that I have trained this guy once, yeah? I have trained this guy also once. I have trained this guy once. And then the thing that I am using in my neural network is a kind of average of all of them, yeah? So it's somehow the average of everybody that I have trained. Clear? Now I have all of those weights here, and then if I want to use this neural network, I don't do any dropout anymore when I want to just do evaluation. I just put my data at the beginning, I just read the output and see what happens. Everybody's clear how I do the dropout? Yeah.
The weights are averaged, you say?
Actually, you don't need to average them. I'm going to explain how you do the forward-backward, but you don't need to average them. You just do your normal update here, 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 but at the end of the day, it's somehow, I mean, the overall update is like that you have done averaging, okay? Because in this one, your weights that are connected from the second input to all of these neurons are not getting updated, right? Because you drop them out. When you drop them out, they're going to be 0. When you move backward, the gradient is going to be 0. And it's not going to get updated, right? The next time, this is going to get updated. But this time, these weights are not getting updated, right? And this is going to happen all across your neural network. You know? And then at the end of the day, it's like, OK, this one that I computed and this one that I computed, somehow I averaged them out. And now I updated my neural network. Okay? Clear? Yes?
Well, let's say I'm looking at a neuron that gets deactivated during the forward pass.
This one, for example.
Okay, yes.
Yeah.
And then how does its weights get updated when it is a backward pass?
Basically, they don't get updated in that particular instant.
Oh.
Yeah, but doesn't matter because you are going to do too many forward-backward, yes? In each of them, you're just randomly choosing some of them, right? And then at the end of the day, at least in one of them, it's going to be selected, right? Okay? So everybody's clear about dropout? How we do it? So this is the idea of dropout, as I told you, and you might wonder why this is working. As I told you, basically it's heuristic. There is a concrete discussion behind it as well, but we just need to know the heuristic. And as I told you, it's like you're randomly choosing a subset of your weights in each forward-backward, and then you are updating your weights for gradients computed over that reduced neural network. And each time that you are doing it, you're doing it in one randomly selected reduced version. And then at the very end, you somehow are doing a sort of averaging over all of them. Okay? Now, one point here that's going to make a kind of connection to what we have seen before in this co-adaptation or overfitting in general is that the whole overfitting comes from the fact that we have too many weights, right? And what we do now is that we want to get rid of some weights, and this dropout is doing that for us, right? Correct? So this makes sense that dropout is helping with overfitting, but there is one crucial question that you might ask me, and that is that why we do it randomly, right? So why we are randomly dropping some weights in every forward-backward, so why we don't just choose some weights, get rid of them, and then we update. We keep on the training forever. The point is that when you select one reduced version of your neural network, you cannot guarantee that that one is a good one, right? And how many of them you have? Exponentially large, right? If you want to choose 2 numbers out of 10 numbers, how many of them do you have? 10 choose 2, right? Now, 2 out of 100. 2, or not 2, like 5 out of 100, and then make it 10 out of 1,000. So it's exponentially increasing, right? So if you want to just count the number of cases that you have, it's impossible. So what you do, you say, okay, I do not have the computation, so I randomly in each iteration, I just use one of them. And then if the good one shows up in between, hopefully that good one is going to help me in the whole average. So it's going to just drop the whole impact of overfitting in my neural network. Clear? So, but this is just a heuristic one. You need a bit of math to just project it into a real analysis. But just want to give you the idea why dropout is really working. Any questions?
So is it like each node that has 50% of chance of being in?
Yes.
Oh, I see.
Exactly. Not 50%. I mean, you choose the probability, but for example, 50%.
Because if we choose, for example, 50%, okay, so if we choose a probability P of being,
Yeah.
and you have a lot of nodes, and have the typical.
Exactly. Exactly.
Number of
Exactly. This is the whole idea, right? So if you, for example, want, I'm going to show it in the next slide, but if you, for example, want to have, say, here is, I don't know, 5, you want to have 20% of them active, then you just randomly choose with probability 0.2, right? And then sometimes you choose 1, sometimes you choose 2, but in average, you pretty much choose 20% of the whole nodes, right? Yeah. So if everything is clear, then just to make it obvious for you that nothing is really happening, I mean, at the end of the day, you just choose dropout, and I guess you have already done it in the previous tutorial. Bruce says, I checked it, the notebook, dropout was there, so you already know the dropout module on PyTorch. But how you do it, basically the only thing that is going to change is your forward pass. So nothing is changing but the forward pass. So say, for example, I want to do the training with dropout, and I want to just use some mini batches. So when I choose one mini batch, I mean, in the classical case, I just go forward, backward, and then I compute the gradient. But no, nothing going to change here. The only thing that is going to change is that when I do the forward pass, I drop out a couple of nodes in my forward pass each time randomly. Okay? So if I want to make it concretely for you, say I have L different layers, and then I want to just choose, do the dropout here. So the first thing that I'm going to do, I'm going to generate some mask for every single layer. Meaning that, like looking at my input layer, I'm going to have one vector S, and this vector S entries are either 0 or 1. Okay? So if this is my input, so this is, say, x1, x2, till xn, then I'm going to generate one vector. This is vector S, and that vector S is s1, s2, till sn. And these guys are either 1 or 0, right? And then those who are 0, when they get multiplied to the corresponding x's, they are going to turn it off, right? So how I choose those values of s, I basically just flip a coin. Yeah? Just generate some random 0 and 1, 1 with probability PL, 0 with probability 1 minus PL. And you might guess that, okay, we should call PL something, but usually we call 1 minus PL the dropout probability, because this is the probability that we are throwing away the node in that particular layer. Okay? So if you just generate this S independently for every single layer that you have in neural network, the only difference is that when you do the forward pass, before we just go for the next layer, you just multiply the output of that layer to that particular mask. Right? And then that's going to be this, nothing else. So this is going, say, for example, S, I show it with mask of the size of the layer with probability PL. And then the forward pass is exactly as before. This is the exact forward pass that we had before. We just start with the first layer. And then each time we add the dummy variable, we do the linear transform activation. And then we keep on going till we are over. And the only difference is that at the beginning of using each layer, we are going to generate that mask at random, and then we multiply that mask to the output, right? So this is what the dropout module in PyTorch does for you. Okay, this is the only thing. And then the backward propagation is exactly as before, and you might say, okay, those weights which we have dropped out, they shouldn't get updated, but this is very easy for you to show that once you do this forward pass, when you calculate the backward pass, the gradient components of those particular weights is 0. And because of that, they do not get updated. So moral of the story, you don't need to do anything for the backward. Just do the backward pass as before. Clear? So one last piece of trick, which might sound a bit crazy, but if you got the idea, I try to explain heuristically for you about this averaging idea, then this guy makes a bit of sense for you. So once you do the training and it's over, completely over, then at the end of the day, usually we do this. So we're going to get that weight, this weight of the particular layer, and then we multiply with the chance of not being dropped out, remaining, right? And the reason you might understand it if you think heuristically. The reason is that, as I told you, we are somehow doing averaging. And when we do the averaging, every single neuron is in that layer is either with probability PL inside that, so it's going to participate in the whole process with probability PL, and it is going to be dropped out with probability 1 minus PL, right? And now, if I want to average, so I want to average my weights over all the cases, then I would say, okay, WL get multiplied to this guy, and when they are not participating, the corresponding weight is 0, right? So it's going to be 0, and then this guy goes off, so it's 0, and now your expected value is this one. Yeah? Again, this is intuitive. It's just based on observation. We tried, we saw that PL, when got multiplied to this one, is going to give us the better result, and then we put it there. But the intuition is that one. Okay? Yeah.
For this one, are we only computed for the one that we didn't drop off or average?
Actually, this is the point, because you can think of every single neuron in that layer that is there with probability PL is not there with probability 1 minus PL. And since you do it in every forward-backward pass randomly, then practically this is really the case. Yeah? Yes?
Okay, for example, we are going 3 times forward and backward.
Yeah?
And at the end of the day, we want to say that what is our weight.
Yes.
How can we define that weight? We are just saying that some kind of...
No, but you initially start with the complete weights, right? Randomly generated. Then you turn off some neurons, you go forward, backward. Then when you update, say you update now. When you update, the gradient going to update only those weights which had been there, right? Then again, randomly you change, and you again go again forward, backward. Then again update. Now you only update those which had been in the second
So they
pass.
are sequential, am I right? The process is sequential.
Yeah, of course, like the normal training. The only difference is that we're just turning off in each forward pass some.
And one of the tweets which we speak about the overfitting is that, for example, if we could estimate how many hyperparameter we need and something like that, it would be really good.
Yeah.
And then we say that's a little hard.
Yes.
But this is exactly what we do for this one. In this one also we try to turn off some hyperparameter, try to understand it.
We are actually, I mean, you can think of it like that, but we are not really doing anything to hyperparameter. We fixed the hyperparameter. The architecture is fixed, right? The only hyperparameter that we introduce is this PL here, right? You choose PL and everything is going on. Yeah?
Does it work like that?
Like what?
Like we are tuning the number of hyperparameter, but dropping.
Somehow. This is the one that I told you. Yes, you can think of it like this. Not really tuning the hyperparameters, but what you can say, you could say that, okay, if I have a very large neural network, then this is very dense. This is full of, weights. And then And then what I do know is that the whole issue of overfitting is that I have too much of those lines here, right? But if I do know which one are the worst one, the useless ones, I could just get rid of them, right? And then when I do that, then I am somehow getting into a sparser model. And this model is going to work for me because this is not anymore to do overfitting. But the issue is that I cannot find out what is this one, right? So just think of this realistic neural network and say you want to get rid of, I don't know, half of the weights. Then you potentially need to just search about 2 to power number of weights that you have. You know, this, I don't know, like M say, or M, yeah. M say is the total number of, so 2 to power total number of weights. And I told you like this guy is order of 10 to power 5 or something, at least, yeah, right? Then you need to have such a search. This is impossible, never ever, right? You can never do it. So what you do is just say, okay, I randomly turn off half of them, and then it's like I am just trying randomly a couple of these guys. And at the end of the day, I get the average of them, and hopefully that one is much better than just going for the dense one.
Yeah. And what in practical, what is the amount of PL?
I'm going to show it right here. So this is going to be the next thing. Okay. So in practice, when you want to do it, you can simply use this dropout module inside neural network. You look at it as a kind of layer. So once you have done the, say, for example, linear layer, you can just right away add it, and then it drops out for you, and then you need to choose your probability. Usually for the input layer, we keep it high, so around 80%. So we keep most of them because we do know that data is impacting a lot. But for the hidden layers, we usually put it around 50%. But this is, again, a hyperparameter. You need to play around with it, right? But that one, you can do it with validation. This is possible. Clear? Everybody's clear about dropout? Cool. So one thing here about dropout, one last thing is that now, I mean, you probably have noticed this, but now in this case, your neural network is a bit different when you are doing training in the forward pass. When you are training or you are doing evaluation. When you are doing training, you randomly, drop out some neurons, right? But when you are over with the training and you want to evaluate, you don't do it anymore, right? Clear? Right? So this is why if you check your second assignment, I told you like put this .train, .eval in the PyTorch, because when you put .eval, you are telling the PyTorch that you are not doing the training anymore, so just use all of them. So if you don't use dropout, for example, or batch normalization, this really doesn't change anything. As you did in your assignment, you didn't use dropout or batch normalization, so you shouldn't see any difference if you get rid of that .train. But in practice, when you use these guys, you need to use that difference. Okay? Everybody's clear? So, any questions on that? Okay, if you got no question, then let's just have a 4 minutes break, and then we start with data, right? Okay, shall we go on? Okay. So now, let's get into this part of data preparation. So this is some part that I added it up as I mean, usually when I design a course or teach or do whatever, I always think of myself sitting there the first time. So this was one of the things that I always, when I started with machine learning, was curious about. I didn't know clearly what they are saying. So I tried to make it clear for myself. Hopefully, it also makes it clear for you. But this is not really machine learning. This is data science. Okay, so we want to talk a bit regarding about the data. And I'm going to keep it short, but there are courses on data structure, data science, and things like that, which you can take if you really want to know more about this. So one thing that is really happening in practice, like if you do a project from scratch, then you're going to see that most of the time the thing that you are doing is that you are dealing with the data. Like you're just making it clean, and then you are getting rid of bad data and outliers, things like that. And usually when it comes to implementation of the neural networks or machine learning solutions, you really do know everything that you need. And they are most of the time available to you pre-implemented. The thing is that this data is the challenging one. Now, the whole idea of this part is to just give you some idea about the data itself, how we look at the data in machine learning. This is one thing. And the other thing is data preparation, meaning that getting a raw data, how you can deal with the kind of good data which helps you train that underlying model. So this is going, as I said, to be very short, but hopefully it just gives you the main idea that what you need to look for if you're really dealing with that in your project or in future. So yeah, one thing that, I mean, I just made the whole of this discussion motivated by going through the idea of data augmentation, okay? And what was the data augmentation? So I told you this is one of the approaches that we can use in order to get rid of the issue of overfitting or somehow help the overfitting. So we are going to talk about this, but this is not the only thing that you can do for data pre-processing. Many times you do data cleaning. This is a practical thing. Like you get your data, you find out, you just do some analysis to find out what is the outlier. Sometimes you even use a neural network or a machine learning model to do that job for you. This is another thing. And then the other thing is that you might do some sort of transform. So many times, those of you who have some background in signal processing, you do know that like audio signal you get in time is not very good. What if I just change it to the frequency domain, right? I just calculate the Fourier transform. I don't know. It's an image, wavelet transform, something else. And that guy is going to work better with the neural network as compared to the original data, right? So finding out what is the transform is also one other thing. Dimensionality reduction, we're going to talk a bit about this when we get into the autoencoders. But potentially, if you have a very big data, then you might deal with some ideas to get that data. Just compress it and get out the main features of that data, and then you give it to a neural network, right? So this is another thing that we do, dimensional reduction. This is a kind of unsupervised learning problem in general. And then we're going to discuss a few of them today here, but hopefully this give you the background that you need. So let's get with the data augmentation, which was the thing we talked about before. So the whole idea of data augmentation is that you have your data set, and as I told you, you're not going out to collect more data. So you have that data set. What you want to do, you want to get that data set and increase the amount of data that you have, which might sound a bit crazy, but if you think of practical examples, you really have examples like that. So say we have one, as I said, data set of cat and dog. What you can do, basically, as I said, just do some transform that you do know that they are not going to harm the image of cat and data, and all of them going to keep the image to be cat and data, right? Now, if I want to make it a bit more concretely, maybe I can write it down in this form, so I can say that I have a data set, and that particular data set D is a combination of course, a bunch of data points, and they're labeled in this particular example, right? And these x's are the pixel vectors of image of cat and dog, right? And those v's are basically label of being cat or dog, correct? So this is your data set. Now, say I give you one particular function a. So I give you this function a. What is the feature of this function? It's going to get one image of dimension n, and then it gives you a transform version of it. So it's still in dimension n. And that guy is still the same image that you had. Okay? So you get your x1, and then this function gives you x hat, and that x hat is still cat when you give cat to it. If you give dog, it's still dog, and so on. If it happens that you give one x, one of your images here, into this function, and then you get out of this function some x hat, which is not inside this data set, what you can do? You can get that x hat, put the label cat next to it, and add it to your data set, right? Correct? So you're expanding now your data set. You get your data set, you add the new transform image and the label cat into it. Now you have one more data, right? And you can try doing it over and over. If you have that magic function, A, you give all the images that you have in your data set, and then you check the output. If it is not inside the data set, you just add it to your data set with the same label. Correct? So this is the main idea of data augmentation that we can do. So how can we do now that function? So probably you do know it for many practical examples. Like if you're dealing with an image, as I told you, any rotation, any linear transform of that image is still a cat, right? If I get the cat rotated, I don't know, zoom it in, zoom it out, just shift it up and down, it doesn't change the fact that this is a cat, right? And I can give all of them to my data set with the same label cat. And I'm increasing my data set size. So this is one thing. So basically what I need to do here is that I need to multiply everything with one particular matrix, and that matrix is the matrix that does the linear transform for me to keep the same image transform. But in general, if I do augmentation, if I expand my data set with this idea, so I just try to find out one function A, and then get this function, give my data into the function, and get the new data. This is what we call it augmentation by engineering. Why engineering? Because I do need to know what is this function. I need to engineer the function. Like for image transform, I need to find out the right A, like the A which does not harm the image, only it rotates the image. I need to find that A first, and once I found that one, then I can apply it on every single image I have in my data set. Correct? So there are a bunch of examples of augmentation with engineering. For example, if we have images, as I told you, I mean, you can do those simple geometric transforms, like rotating, shifting, things like that. But you can do much more advanced things. For example, you can just change the filters, so the sharpness of the image changes, or for example, you can change the brightness of the image. You can add a bit of background noise into it. So you can do lots of things that are not going to harm the original fact about the image, that this belongs to that class, right? If you have, for example, one thing else that you can do, you basically can train a neural network to do it for you. And we're going to see it in chapter 8. Like I can make a neural network which gets an image of a cat and gives me a transform of a cat. Yeah? You can do it. Yeah? You might think, right now, I guess you find it quite doable, right? And this is like the beginning of the idea of generative models, right? So you see that generative model sounds like no crazy anymore to you? It's a good sign? Yeah. Okay? So there are also other things. For example, the audio signals. You can use audio signals, different transform on them. Like again, you can add background noise. This is a typical thing that you do. You can change sampling rate. You can just do some sort of shifting on your audio signal. All of those things. Anything that doesn't change the fact about your audio signal. About the text, you can do the same thing. You can just do random replacement. You can just make, a bunch of punctuation changes, things like that. So for any particular application, when you get into that one, you can simply read a rich literature on how you can get different versions of, or how you can augment your data set. But in all of them, you really need to just engineer your augmentation, meaning that you need to really focus on the task that you are doing. So it's image processing, audio processing, text processing, anything like that. And then when you found out that one, then you do know what kind of data set you have, and then you do the transform based on that. So you really need to engineer that. This is one thing. One thing that you already have heard of in the first assignment is the idea of synthetic data generation. And synthetic data generation, what does it mean? It simply means that I'm not going to use the data that I have in order to generate a new data. I want to generate data out of my pocket. Yeah? I don't want to really do it. I just want to do it out of some random thing. How we can do it, we already have done it for the dummy projectile example, right? So how did we do it? We said, okay, we do know that the distance is going to be related to the velocity and height in this form. So now if I just generate a bunch of random heights and velocities, which are meaningful, of course, like velocities must be positive, heights must be positive, I just randomly generate some positive real numbers and give them to this function, it's going to give me the corresponding label, right? Now if I want to make a data set, I can make it as big as I want. Just I run that random thing as much as I want, and for each of them I do know how can I find the corresponding label, correct? So this is not augmentation, this is synthetic data generation. Because I do know how I can make the data, so I just start from a random seed, which is those random height and velocity, and then I generate as much as I want. Correct? Yes?
This supposes that we know the law, so like the goal of the end would be like to do it automatically or something, right?
Yes. I think next slide I talk about this, right? But this is the first argument you might give. But in the next slide, probably you just revise your argument. Okay. So now, just to make it clear once again, so when we talk about synthetic data generation, we basically start from a random seed, as I said, and then we just simulate the whole process to get the output, or the whole process of generating that data. So you start from the random seed, and we pass it through that process, then we get the whole data sample, right? And then we add it to our data set. This is one thing. But when we talk about the augmentation, we simply know the function which operates on one data and gives us another data of the same time, right? Same type, right? Cat image, it gives us a cat image. Dog image, it gives us a dog image, right? We can even do this, like if you can make a kind of function which gets a cat image and gives you a dog image, it still works, all right? Yeah? Because you get all the cat images, you generate dog images, and then you add them with label dog to your data set, right? But as long as you know a function which gets one sample from your data set and gives you one other sample from data set with valid label, you can use that function to do augmentation, right? So two different things. Augmentation is different from generation. Now, as your friend said, like initially all of us would have said, like how we do the synthetic data generation, we should know the physics of the story, right? So it's really a mechanical problem. We just simulate the mechanics, dynamics of the problem, then we just generate some random seeds, and then we do it. But nowadays, all of you know that you can start from a random noise and generate human face, right? By generative models. If you wonder yet, you're going to wait for chapter 8 when we do it, okay? But you can really do it. You can start from a random noise. I mean, none of you check the new tech news? Have you heard of generative models, diffusion models, GANs? So there are a bunch of models. So when you're over with this course, you're going to get to them. Like you have all the background and you even know how they work. So there are some sort of models that you start from a noise. You just give a noise to that neural network. At the output, it's going to give you the face of a human being. Just search it online, generative models. And since we have them, if we, for example, want to extend that data set, we can just use that generative model to generate as much cats as we want. Correct? So generative models could even help us in augmentation. So nowadays they are just, but like a couple of years ago, people always think of, scientific simulations only. So that's it. So this is one other point that I told you. So you don't really need to have one transform that gets one sample and gives you another sample with the same label. You could get one sample with one label, get another sample with another label, right? Cat converted to dog. But you don't want, when your data set is only cat and dog, you don't use a function which gets cat and gives you frog, right? Because that is not inside your data set. So as long as you're still within the valid labels, so you can still use it. So cat goes to dog is all okay, but cat goes to horse is not okay anymore, right? So, and given this intuitive illustration, now we are ready to just formulate augmentation and also synthetic data generation formally. So this is going to be the definition of data augmentation. So when you are talking about the data augmentation technique A, this is simply a function. It could be a neural network. It could be anything, any transform, that gets your training data set D, and then it gives you a bunch of samples at the output. All of those samples have valid label. This means that all of the labels that are generated are within the classes that you have inside your data set. And then when we talk about synthetic data generation, we start from a random seed. We don't do anything with our data set, right? We might use our data set to train that. I don't know. I mean, we might use our data set to find, design one S. But when we design this S function, we don't use the data set anymore. Yeah? So this is what you do in generative models. Okay? But forget about it right now. Okay? So here in synthetic data generation, you are not using your data set anymore directly. You're just starting from a random seed and then generate lots of samples. So this is a good thing if we could do it, but not always we can do it efficiently. So that's it. And now one thing that you might notice here in my definition that I have shown you here is that data augmentation, I have defined it, for example, a technique, technique A takes the training data set as the input and returns new sample from data distribution. Yeah? And again, synthetic data, same thing. It's a technique that starts from a random set and give you samples from data distribution. Yeah? And you might tell me that everything here is clear, but the concept of data distribution, what do you mean by data distribution? Isn't data simply a kind of set of bunch of things that we are looking into? The point is that when you when you get into the community of machine learning people, they always talk about the samples that you have or data points that you have inside your data set as samples coming from a data distribution. And you might think that people are just randomly throwing words, samples, data distribution, but no, they are not random words. They're really having some meaning behind them. And my whole purpose in the remaining of this section is to make that meaning for you clear before we start with those practical parts. Okay? Now, those of you who are not interested at all of that, you can take your ears, okay? But trust me, it doesn't harm. It's a really good thing to know, okay? Trust me, it's going to make life much clearer for you. When you read a paper, oh, everything is clear now. So now, what is the idea here about this data, or maybe how people in machine learning look at the data? Okay, say this guy is the one sample from MNIST, right? 20 times 28 pixel, 28 times 28 pixel image, and this guy has a bunch of pixel values, right? I have written the pixel values here. All of these guys are pretty much black. The remainings are white, and this guy, as I told you, is a 28 times 28 pixel image. Every single image, as we talk, is every single pixel here is an 8-bit pixel, meaning that the value of that pixel is either 0, 1, 2, till 255, right? One of the possible integers you can show by 8 bits. Okay? Now, and when you look at MNIST, MNIST has only images that are images of handwritten numbers. But one thing that you do know for sure is that, first of all, MNIST does not include all possible 28 times 28 pixel images. It does not include all of them. Yeah, definitely. If I write down a handwritten 3 right now, and you scan it and you make it 28 times 28 pixel, this most probably, almost with probability 1, does not exist inside MNIST, right? You can put it in MNIST. So it doesn't have mine, so it doesn't have all 28 by 28 pixel images, correct? One other thing is that it even does not have all possible handwritten number 3 in this form, 28 times 28. As I told you, it doesn't have mine handwritten digits, correct? Now, you might think that, okay, the whole number of these things is infinite, but it's not really infinite. Anything that we can use a computer for is theoretically finite, practically infinite. So what does it mean? It means that, like, if we look at MNIST, so 28 times 28 is 784, right? And this 784 is the number of pixels in the vector, right? Now, every single of them could be 0, 1 till 255. So can you tell me what is the total number of such vectors that I could have? Every single guy in this vector, so if I write down any 28 times 28 pixel image, it's going to be a vector of numbers, right? And then it's going to be x1, x2 till x 784. Am I correct? It's 784, right? And each of them could be either 0, 1, and so on till 255, right? So each of them, the number of cases we have is 256, right? Now, how many of such vectors do I have? 256 is when I have 1 pixel. If I have 2 pixels, it's going to be 256 times 256, yeah? If I have 3 pixels, so the total number is this guy to power 784, right? So I have this much of possible 8-bit 28 by 28 pixel images, right? Correct? So this is the total number of images that I could have. You might use this approximation that, I mean, first of all, you can write this 256 to the power 8, and then you take that 8, multiply it, and then you approximate it. Then at the end of the day, you're going to have that much of images, 10 to the power 1,881. I mean, more than that. But that guy is not infinite, theoretically, right? It's finite. You start from 1, 2, 3. At that point, you stop, right? But it's practically huge, right? Now, one thing that is that MNIST, all the tests and training data set, all of them that you have is 70,000, right? Which is less than 10 to the power 5. And if you compare that 10 to the power 5 to that crazy number, you see that by no means you can compare yourself, yeah? You're not even a tiny drop in comparison to the ocean, right? You have that much of images. But one point here is that not all of these images here are handwritten number 3. And I hope that I made it clear for you, because this guy is also 28 by 28 8-bit pixel image, right? And that one is not 3, not 0, not 1, not 9, yeah? It's a cat. Yeah, like a cat, right? So this is not inside MNIST. It could not be inside MNIST, right? Never, ever. Correct? You got the idea? So you have a finite number of images. Not all of them is a handwritten digit, but whatever you have inside your MNIST, first of all, definitely that guy is not, I mean, if you collect all of them, it's not representing all possible handwritten numbers, right? All possible data samples that you could have, Now, people at this point, they started to just think about it a bit theoretically. They said like, okay, say that, I mean, what do we do in math when we don't know something? I mean, we always model it as a kind of random object, right? Some random object that we cannot access to, yeah? And then it could have lots of cases, and we're going to see a finite number of realization, right? So a Gaussian random variable is any real number on the real axis, correct? Most of the time is around 0, but it could goes to plus and minus infinity as well. So people started to think of it the same way. So they started to say that, okay, we have something called data space. And data space, what does it mean? It means that now we are getting out of this universe. We are going to a parallel universe. And in that parallel universe, people can count. People can make sets which are big as 10 to the power 1881. Okay? And in that universe, they are going to collect all of those 28 by 28 images, and they look at it, they say, this is a handwritten number, I put it in this set. This is a handwritten number, I put it in this set, and so on. So they collect that set. That set is the space of your data. The set of all possible, for example, images, which are 8-bit images, and those images are handwritten numbers. Yeah? Quite crazy. We cannot really find out this set ever. Yeah? Maybe for 2-pixel images we can do it, but for very big set we cannot do it. But the point is that we can think of that guy exists, correct? Yeah? In somewhere where we cannot access it right now. So that is what we call it data space. Yeah? And now, what do we have in MNIST? We have 70,000 people of that space. Yeah? How did we get them? Did we do any special procedure? No. We just went out randomly, asked people to write down handwritten numbers. Yeah? We sampled that space randomly. Yeah? And we got those 70,000 sample images. Correct? So this is the whole idea. So this space of data is, of course, not possible to be accessed because this is crazy in size, especially if you get out of, I mean, this one, you get to CFAR, I don't know. You can never, ever talk about that one anymore. But at the end of the day, we can imagine such a set exists. And what we are doing, really, MNIST is just collecting a subset, which is a subset of samples randomly drawn from that space. So this is what we think. So any data set that you have, any practical data set that you have, is much smaller than the space of your data. And because of that, you assume that data set is the collection of a bunch of randomly drawn samples. Correct? Everybody's clear? Yep? Okay, great. So, for example, what you can say that you have, for example, in this example of MNIST, what you can say, okay, there is one machine, so it came from Mars. And that machine, when I press it, it just gets connected to that data space we do not have access to. It draws one, it just gives me one random thing. And when you have MNIST, what you have done, I mean, any data set that you just push that machine as much as you could, and then you get all of those images, right? And then, for example, for MNIST, what I have done, I have just pressed that guy 70,000 times, and it gave me 70,000 of those images, correct? This is not really how I did it. I mean, I went out and asked people to write down numbers, but this is mathematically equivalent to doing that, correct? Now, data distribution is the probability distribution that the machine works with. Okay? So when you press that button, like if you have a Gaussian distribution, what does it mean? If you have a Gaussian random generator, when you push it, most of the time you get around 0, correct? You get less frequency around like high numbers. Same thing with that machine. So if you ask people to write down a 3, they usually write it down in some specific form. Yeah? Maybe some guy just wrote it down a bit rotated or things like that. But most of the people just followed the same pattern. So your data is most of the time around that pattern, right? And because of that, your data distribution is something specific, right? Depending on the kind of data space that you have. So now, again, this data distribution, one good thing that it has, I can forget about data space now, yeah? Because I could say, okay, MNIST image is 2 to power, we said, like 256 to power 784 different images. So I call it that the space of possible images. And then I have one machine here. I just press it. It gives me the images that I want, correct? This is a good thing, but the main thing about it is that, again, we cannot really specify the data distribution. Because how you can say I mean, if you want to describe a distribution, you really need to be able to describe this space, right? So if I want to find out the Gaussian distribution, I need to try that Gaussian generator, I don't know, 1,000 times, and then I just draw the histogram, and then I'll find out the distribution, correct? Now, if I have this size, I need to do it at least 1,000 times larger than this size in order to be able to find out the distribution. I can never do that, correct? And because of that, again, we do not have access to this, but it doesn't harm if we assume it exists. Clear? Good. So one thing that we can say here for sure is that, for example, say MNIST contains 70,000 samples drawn from by this data distribution px, and this px say this is the distribution of MNIST data set. Okay? Now what I can say for sure is that if this guy is x1, p of x1, the density of x1 is not 0, because number 3 exists in MNIST, correct? But this does not exist to MNIST, right? So probability of that happening is 0. Yeah? That never happens, because MNIST is supposed to contain handwritten digits. It does not contain cat. Correct? So you can talk some, very high-level things like this about the data distribution, but what is that guy exactly? Well, you cannot say it. Clear? Good. So now, hopefully next time when you open up a textbook on machine learning or you read a paper or anything, if you see such a sentence like a learner simply means a neural network, has access to a small reference data set, that is the training data set that you have. This one, of empty samples drawn IID from a target distribution dt, you do get what they mean. They simply mean that they went out and collected, that much data samples, and we did it independently. Like, we asked the first guy write 3, and the second guy, we didn't show the previous 3 to him, right? We told him, you also write a 3, right? So we did it independently. It was identically distributed, like the kids were all behaving normal, the same, and because of that, we expect that to be IID. Okay? So this is not a very complicated thing. It's just an alternative way of looking at the data. But this is very important, especially if you get a bit more advanced. Like if you get into generative AI, generative models, then you really need to think about this, about the data in that way. Because at the end of the day, you want to design one neural network which is able to generate one of those samples, right? So you would say MNIST does not contain all of the handwritten digits. So what if I design one machine which starts with those handwritten digits and get trained, and now it just sample from that space which I do not have access to? Yeah? This is what we do in generative AI, but you don't need to confuse yourself right now. We're going to see it later. Okay? So that's it. One last point. In very, very basic data analysis problems, you are able to approximate data distribution. Like, for example, your data contains only height and weight of people. Then if you take so many samples, then of course you can get a rough idea about the histogram of that data, right? But for many problems, like classification, things that we do with big neural networks, we really cannot do it. Okay, so any questions? Was it worth it? Okay, that's cool. Okay, now back to the track. So one thing that I wanted to just end up here with is the practical aspect. This is basically I added because this is useful for your project sometimes when you do it. So the practical aspects, mainly what you want to do in these aspects is that you're going to collect some data, right? And then as I told you, data should be drawn from the data distribution. But how you can guarantee that this is a good sample of your data distribution? So there are some tricks to evaluate that. I mean, it doesn't mean that those tricks going to give you a concrete result. It's going to help you to just filter or rectify your data set. It doesn't mean that they are always working fine. But the main target that you are looking for is that whether you want to check whether you have good representative of your data space inside your data set or not. And sometimes you also want to see whether you can find a sort of transform which just, for example, map your data set into a smaller dimension that helps you find out better representatives in that space. But this is not exactly what we do in this part. So in this part, I basically take you over two tricks for data cleaning. So one of them is the data removal of duplicates, which you obviously do know that. But maybe I just give you an intuitive idea how you can expand into the larger dimension. And then the other one is to just find out the outliers. Okay? So duplicates. The duplicates is the first thing. So if you have one data 2 times inside your data set, this is not necessarily, I mean, most of the time is a bad thing. So why? Because I have this data set and I'm going to do the training over it, meaning that I am going to compute the loss of the output of my neural network, compare it to my label, and then average it over all the data that I have, right? This is the risk that I am going to minimize, correct? Say we're doing full batch rating right now. Now, one thing that happens is that I copy x1, v1 into this data set m times, meaning that I get my first sample, I put it m times more in that data set. Yeah? This is not augmentation. This is not a good idea in general. Why? Because this guy was the loss, correct? So I computed loss over all the points. Yeah? And then when I copy m more copies of x1, the thing that is going to happen is that I am going to have extra m times loss between y1 and v1 as well in my data set, correct? Because I have m more x1 copies of x1. I send all of them over my neural network. All the m times I get y1, and then I compare it to v1, correct? And I add it to that loss. Now this new guy is the sum of all the losses. And if I want to compute the empirical loss, I should divide it by b plus m, right? Because I have m more guys. So b plus m, that b plus m. And this new guy is not necessarily the previous guy, correct? So when you duplicate, you're changing that loss. I mean, if you're sure that doing the duplication is going to help you, because, for example, you do know that in practice, the first data point, the first sample is going to happen much more in this data set, then go ahead and do it. But if you don't know that, just simply copying because some dude told us augmentation is a good idea is not a good idea. I mean, copying is not augmentation, right? Great. So one thing that you should pay attention is that usually when it gets to the data processing, you want to find out whether, I mean, the data set that you are given is containing any duplicates or not. And then this could be coming out of different sources. Like one thing is that some people did a mistake and put something a couple of times in the data set. Sometimes it's a kind of adversarial action. Like somebody wants your neural network not to work fine, so they are going to duplicate some samples too much. Okay? And then they make sure that your neural network is not getting trained properly. And then the whole trick of data cleaning is that you find out what is the which one is duplicate. Yeah? And Usually you need to know a bit of statistics to do that, so I'm not going to open that up. Just give you a bit of example. For example, say you are training a neural network, and the data that you have is age, education, and place of birth, and then what you want to do, you want to find the number of children as the output. So you go ahead, you collect a bunch of data inputs which contains age, education, and place of birth, and you label them with the number of children, right? Now, if you see in your data set too many 22, Bachelor, Toronto, and then with label 0, this is not really necessarily duplication, right? Because there are many people at age 22 in Toronto who have bachelor in science and they do not have a kid yet, right? Correct? So this is a kind of typical data, like it happens a lot. And even if you see the data set and you see that there is not too much of that, you can just copy it as much, because I do know all of my friends, same thing, right? So I'm going to copy it. So this is not duplication, but if I have a data set which just gets age and the height as the input, and then it returns, I don't know, the weight as the output, it's not very possible that I see this number 48 as the age, 176.42 as the height, and exactly 73.31 as the weight a couple of times, right? So I mean, it might be like some people with that age and that weight, that height have this weight, but it's not always the same thing, right? So it should be around it, correct? So then here you obviously detect a sort of duplication, correct? So one thing that you might come here to your mind is that here and here you just compare these two examples, and here you concluded this is not necessarily duplication, this is duplication. Why you do this? Because somewhere back of your brain you think that, okay, these data, the data has been collected independently. So we went out and asked people, random people independently, what is your height, what is your age, what is your weight, right? Because of that, you don't expect that two independently chosen people have the same parameters, exactly the same. It doesn't make sense to you. And this is basically what you have in your mind as a kind of a statistical look at the data. So you have it back of your brain. The only thing that I did, I helped you to take it up, right? You get it out of your brain. So just to tell you that this statistical point of view is not a kind of crazy thing. The other thing that you might have inside your data set is an outlier. And what is an outlier? Outlier is one particular data point which is in abnormal distance from the other data points, okay? And one example is this guy. For example, you got into the physics lab, you did measure the currency and voltage, and then you just plot them against each other, and then you expect it to be pretty linear because of the Ohm law, but then you see this particular guy here, right? So this is a kind of outlier. Yeah? Now, if it is the physics lab, you do know that this is simply your measurement mistake, correct? But it could be also some sampling from outside world. And then again, you see that most of the data is happening around one particular outcome. Then there is one data out of it. Yeah? You don't say that there is necessarily a mistake, but what you could say is you could say this is not a typical thing that I should see. Yeah? So this is what we call it outlier. And now if you go ahead and train with the existence of this outlier, you might have your line to be trained a bit higher, meaning that you might get the wrong resistance of that particular component you are experimenting in the lab. So finding outlier is a kind of crucial thing. I mean, sometimes people even train a neural network to do it for them. But we're not going through that. The only thing that I want to let you know is about the kind of tests that we have. One of the tests is to just detect what we call it univariate outlier. And univariate outlier simply means that when you look at one single point in the whole data point, one single entry of your data point, you immediately understand that this is an outlier because you compare it to the other entry or the same entries in the other data points. So what is the example, for example? Say, for example, you're just collecting the heights and weights of some people, right? To just train one neural network or one model, which just gets the height, gives you the weight, for example. Yeah? Not a big deal, but say you are doing that. And then you are in very bad luck, and out of your samples come Sultan Kuzen.